Hello, everyone. Welcome back to the AAS YouTube channel, and this is the good stuff. This is the AAS Author Series, and I'm super happy to have Rana Ezzeddine with us today. Hey, Rana.
Hi, Frank.
How are you?
Thank you for having me.
Oh,
I'm
well,
very well.
Thank you for doing this. It's really great. I think it's a really lovely paper.
Thank you.
So we're gonna walk through it. What's your geolocation? Where are you at?
So I'm currently in Gainesville in Florida. I have moved here on January, actually, the 1st of January, and I started this semester, my first semester as an assistant professor, and then COVID happened. So it's been quite an interesting semester.
Are you teaching this semester?
This semester in the fall, no, I'm not teaching, but I was teaching in the spring. So I chose to teach my first semester just to get started. I was going to be busy anyway, but this semester I'm not. So I'm free to do research with my students and with my group. So that's very exciting.
That's awesome. That is that's a great tree of life there over your shoulder. Is that what that is?
That is a tree of life, and it always triggers some conversations about people saying, why don't you have an astronomy photo behind you? But you know, we're all part of this tree of life, so it's very interesting. Thank you.
Indeed. And we know where those elements come from.
Yes, exactly. We should probably have a lower part from the tree of life, starting all the way back from the Big Bang to just extend it. Yeah.
So Rana, what do you like to do for research in general?
So I'm both an observer and theorist of stars. I started with my PhD doing more theory of the stellar atmospheres of stars, basically study the absorption lines that we observe in the spectra of the stars. I will talk a little bit about why that is important during the paper, actually, which has a little bit of a theory part. But I am also an observer, and I'm mainly interested to observe metal poor stars, so stars that have very deficient metals in them, especially iron. That's how we quantify it. The reason for that is because these stars are the fossils that are remaining fossils from the early universe. And so whatever enrichment events has happened in the early universe in terms of chemical elements production, they have been retained in these stars. So in my work, I try to observe, analyze, and then interpret the observations of these types of stars.
Very cool. Very cool. Yeah. And that'll take us to this lovely APJ paper, the R-Process Alliance, first Magellan Mike release from the Southern Search for R-Process Enhanced Stars. Rana, take us away.
Thank you. So this is actually one of my first papers on metal poor stars that particularly works on the R process. I've worked on metal poor stars in different aspects, somehow from the theoretical part, and I've also worked on ultra metal poor stars. But the R process, I'm sure all of you have heard a lot about it recently. It's been in the news because it has a very interesting story. So let me start by giving some kind of intro to the topic and why we want to do a data release about these types of stars. Okay. As you know, we know a lot about the formation of the elements that are found in the periodic table, which make up all of our universe. However, particularly the lower part of the periodic table, which involves the heavy elements, particularly that produced by the R process, has been less known than the production from different other processes forming the lighter elements. And for the longest time, people assumed that the R process, which by the way stands for the rapid neutron capture process, from the name, it requires a huge flux of neutrons to be injected onto a seed nucleus, which forms the heavier elements and then beta decays into stable elements. For the longest time, people thought that this could possibly happen in core collapse supernovae. However, evidence and people doing core collapse supernovae have been telling us for the longest time that it's unlikely that core collapse supernovae are the dominant sites of the R process formation. And then other theories came along where what about neutron stars, or binary merger, or mergers of binary neutron stars, which would produce, as you imagine, a huge flux of neutrons. This could also be a very, very nice site for the R process. However, before 17th of August 2017, the astronomical community had not observed the merger of two neutron stars. But until that date, when LIGO has detected the first gravitational wave, and then all of the telescopes in the world looked at this event, it became very exciting that we observed for the first time such an event. Now, how does that relate to the R process? We believe that within or after this or during this event, the R process elements are formed, and we were able to see for the first time a kilonova spectrum, which confirmed to us that this is due to heavy elements being formed and the beta decay and radioactive elements being formed during the binary neutron star merger. Now, this is all very interesting, and people for the longest time have been trying to find these stars or these elements that are found usually in metal poor stars. Now, why do we need to look for, or why do we look for metal poor stars particularly? It's because these are, we consider them the fossils of the early universe. So metal poor means that the universe did not have enough time to form enough elements, and so this means that these stars are quite old, and because they were low mass, they have survived until the present day, and we can find them in the Milky Way halo, in dwarf galaxies, etc. And what we do is we try to, and what we're doing in this paper is we try to find these R process enhanced metal poor stars. And what that means is that they are metal poor by definition. So their iron to hydrogen abundance is lower than, let's say, -2. But they also show enhancements in the R process elements, particularly europium, which is a representative of the R process itself. And so, yes, exactly. So the way that we define or identify these stars as R process enhanced is by comparing the ratio of europium over iron. And we usually divide these into 3 groups. Ones that we call the R2 or highly enhanced R process stars. And in this paper, we find 10 new of such stars. We also find 62 moderately enhanced or R1 stars, where the europium over iron lies between 0.3 and 1. And then we also found 17 limited R process enhanced stars whose europium over iron is less than 0.3. And I will talk later on of what is the astrophysical significance of these types of stars. And so in this paper, we went out to try to find, as I said, these R process enhanced stars because they are very interesting. And the way we do this is a little bit of an intricate or a lengthy process because as you know, telescope time is quite expensive. We cannot just point our telescope randomly and observe for hundreds of hours. Yes, these types of stars. So we go through multiple vetting processes. The first one is where we look at, for example, photometric surveys or low resolution spectroscopy surveys that are coming from, for example, RAVE or SkyMapper or LaMost. These are interesting because inside these surveys, we use what is called a calibration or photometric calibration metallicity. So we determine a first order metallicity of the stars. And after we've determined these metallicities, we then have vet down this large list of stars that have been observed by these surveys. And we then look for the brightest ones among them, because if we are to find an R process star, we want it to be bright enough so that our telescope will be able to determine as many of these R process elements as possible. So once we've vetted these two conditions in terms of metallicity, so we choose the lowest metallicity stars and the brightest ones available, we then follow them up with high resolution spectroscopy. And in this paper, which is, by the way, the third data release searching for the R process stars, we used the Magellan Clay telescope, which is in Las Campanas Observatory in Chile. So I spent about 30 nights in Chile on this telescope, observing lots of these stars until we found all 141 of them that were interesting.
Cool. Very cool.
Yeah. So if you would like to go to figure 1, or maybe we can talk a little bit about the, yeah, we can talk about figure 1. So after we have observed these stars, we want to analyze them. We went ahead and analyzed them. And the analysis or spectroscopic analysis of high resolution spectra goes through multiple steps. The first thing we do is obviously we normalize the spectra, and then we determine the radial velocities, which is a very important step because it aligns our interesting lines with the rest wavelengths. And there are multiple ways, obviously, to determine radial velocities of stars. The exoplanet people would know a lot about this, but one way we do this is by determining the shift, basically, like a Doppler shift. Of our stars relative to template spectra, and we determine the radial velocity in kilometer per second. So here what you are seeing on the x-axis is the radial velocities, the heliocentric radial velocities that we determine spectroscopically. And we wanted to make sure that these radial velocities are accurate, and so we compare them with another telescope that has done greatly with radial velocities, which is Gaia. And so as you can see that most of our stars lie within a mean deviation, or lie around the difference 1.93 kilometer per second, which is an acceptable difference between radial velocities, and the sigma is about 3 kilometer per second distribution around this difference. Now you can also see, interestingly, that we do have some outlier stars that go up to 20, 40, and 60. This is not usually an acceptable radial velocity difference, and we attribute, or not only we attribute, but we actually looked further at these stars, and we found that in many of their strong lines, such as the H alpha and H beta lines, we can observe double lines, which means that they are spectroscopic binaries, which is very interesting. However, we did not consider these stars further in our sample, because the main aim is to identify our process elements. And we know that binary stars don't necessarily, well, binarity has nothing to do with the R process itself. It can simply not produce a flux strong enough to induce the R process. And so we ignore these types of stars, and we only take those which do not show any binarity.
Okay.
And then after we shift our spectra with radial velocities and determine the radial velocities, we have to do the most important part of the analysis, I would say, which is determine the stellar parameters of the star. Stellar parameters highly affect the abundances that we derive later on in our analysis, or any spectroscopic analysis. However, stellar parameters are somehow problematic, and this is where my theoretical hat comes in, because the stellar parameters, by the way, what I mean is the temperature, the effective temperature, the surface gravity of the star, the metallicity, and the microturbulent velocity, which is a fudge factor that we assume correlates with the different velocities happening in the atmospheres of the stars. So as I said, we have chosen mainly bright stars, and so most of the bright stars are giants, and you will see later in the HR diagram, they lie on the red giant branch. And these giant stars usually have extended atmospheres as compared to, for example, main sequence stars, and therefore we would expect them to have some kind of random velocities in their atmosphere. atmospheres. So ideally, the best way to analyze these stars would be using model atmospheres that are fully three-dimensional. However, as this is not not computationally feasible at the moment, we assume 1D atmospheric models, but we assume that there are some velocities to be accounted for in our models that we basically account for using what we call microturbulent velocities in our analysis.
Yep.
And so the typical way, or the most common way, that the community determines these stellar parameters is by using an LTE method, which stands for local thermodynamic equilibrium. And this means that we assume that the star to be a beautiful black body that has no non-equilibrium effects in it whatsoever. Now, as you can imagine, this really makes our analysis and our lives much easier, because this means that we can assume the stratification of the atmosphere of our star to be only dependent on each layer of the atmosphere, to be only dependent on temperature and pressure and electron density. And this will make things easier when we determine the level population of the different elements that we're determining their abundances. This is okay for stars that are, again, small, compact, for example, like main sequence stars, because we can assume that those stars are in equilibrium. However, as I mentioned before, red giant stars are not really in equilibrium. They have lots of extended atmospheres. Additionally, metal poor stars are stars that are deficit in metals, which means that they cannot induce equilibrium in their atmospheres because there's not enough electron donors in the atmospheres of these stars. And so all of these reasons tell us that LTE is not a very good assumption to determine the stellar parameters of the stars. And so in this paper, in addition to determining the stellar parameters in LTE, we also use two other methods to estimate the stellar parameters. The first one is called a corrected LTE stellar parameter, which is based on a work done by Anna Frebel et al. In 2013, who calibrated the spectroscopically determined temperatures using photometric temperatures. Now, photometric temperatures, which are determined from the colors, are usually more accurate, or have been shown to be more accurate than LTE for the case of for cool stars especially. And so what they did in this study is they came up with this relation, which you can see here in figure 1, where you can determine your photometric temperature, which is the corrected temperature, as a function of your LTE temperature by applying this equation. And I can show in figure 2 how these differences, or how does that play as a difference when we compare the LTE to the corrected LTE parameters. So what you see here is the delta temperature, delta log G, delta metallicity, and delta microturbulent velocity. So the differences between the, for example, on the first side of the first panel, you can see FR13 corrected. So these are the temperatures that have been corrected using the Frebel 13 equation as compared to the LTE. Now, in order to make this clearer, or in order to visualize the differences better, I divided my stars based on their stellar parameters to show that stars that are cooler than 4,500 Kelvin display the largest differences as compared to LTE, whereas those, as we go toward hotter stars, the differences become smaller and smaller. And so you can see that assuming LTE, in this case, or strict LTE without taking into account these corrections, can cause a huge difference, up to 250 Kelvin or even 300 Kelvin. And this can highly impact our abundances later on. Now, I did a similar analysis in non-LTE. So as I said, that non-LTE is the opposite of LTE. So that is taking into account the full non-equilibrium status of the star and solving from zero. So not assuming that the star is a black body, but rather assuming that any transition that takes place in the star, which causes an absorption line that we see in a spectrum, is caused by a complex web of multiple transitions affecting the single transition. And so these types of calculations are more expensive, as you can imagine. So in LTE, we press one button on our laptops and we get an abundance after a few seconds. In non-LTE, we have to wait for 3 to 4 hours, depending on the stellar parameters of the star, in order to get a single calculation. And we ideally need a computing cluster that can do multiple models so that we can check which model is actually the best that works for our star.
And I imagine you would also be sensitive to the transition probabilities, or if you like, the rates that go between the different levels.
Absolutely. So in non-LTE, that is one of the more difficult, or why not a lot of people like to venture in non-LTE, is because we highly depend on, or we are highly dependent on the atomic data that we use in our calculations. So yes, we need to take into account every single radiative transition that can take place in a star at a certain temperature or gravity. We also need to take into account all collisional transitions. So for example, in my iron model atom that I used to determine these stellar parameters, I have 2,000 energy levels of iron and millions and millions of transitions that I've carefully put together using the latest atomic data available to try to create the most up-to-date model atom, because this would highly affect our abundances. So it's not fun when you think about it, but actually it's very important. And this type of comparisons shows us why it's important for us to venture down that lane, even it's not that easy to do.
Mm-hmm.
And so, yeah, back to figure 2, I showed the differences relative to the Frebel correction, but when we compare to the non-LTE, so this is a difference between non-LTE temperatures relative to LTE, you can see that even though they are slightly smaller than the photometric corrections, we still have differences mostly pronounced for the cooler stars, which can reach up to 100 or 150 Kelvin in difference, which can also affect our abundances. Now, the most interesting to me difference between LTE, non-LTE, and the Frebel corrections is that for gravity, which is the second panel on the right. So you see that also I divided again here my stars into stars that have surface gravity below -1.5, which means they are on the upper brow, so they are red giants or highly evolved stars. And you can see that the corrections relative to both non-LTE and the Frebel corrections are also mostly pronounced for these highly evolved stars. And the reason for that is because when we determine the gravities spectroscopically of the stars, we use neutral iron lines, and these neutral iron lines are highly susceptible to non-LTE effects. So they are really not formed in non-LTE in the atmospheres of this, pardon me, they are not formed in LTE, they are formed in non-LTE. And so this is why we observe these larger differences up to 1.5 dex, which is crazy. I mean, this can change the whole evolutionary status of your star. But additionally, for gravity, we had the opportunity to compare to Gaia, because Gaia provides us with parallaxes, and parallaxes are tightly correlated to the gravity of the star if we assume some kind of temperature. And so we were able to compare the LTE gravities that we determined relative to Gaia determined gravities, which are independent from spectroscopy. And you see that the corrections are very large relative to LTE. But interestingly, our non-LTE gravities and the Gaia gravities actually match quite nicely, which tells us, again, why we need non-LTE, because the Gaia method is to determine gravities, it doesn't depend on spectroscopy, it's completely independent. And yet when we compare it to a full non-LTE analysis, we can see that it matches quite nicely. And then we did the same for metallicity. So you can see in the lower panel, and also for the microturbulent velocity. I will talk mainly about metallicity because it's quite interesting. So the metallicity of the star, as I mentioned before, we always compare our elemental abundances relative to iron. And this relative to iron, which is quite important, comes from the metallicity. So we really need to determine this metallicity correctly for stars to infer later correct chemical evolution of our stars, or where our chemical, or where does our star stand in terms of the chemical standing. And so you can see that I also divided my stars here based on metallicity. So stars that have a metallicity lower than -3, so we call them extremely metal poor stars. Those usually display slightly larger corrections for both the Frebel corrections, but in non-LTE we have also larger corrections relative to LTE that can reach up to 0.6 or even 0.8 dex, which is quite huge. And so for the rest of this paper, we decided, as inspired by these plots, we decided to adopt our non-LTE stellar parameters to determine the rest of the abundances of our stars.
Okay.
And so we proceeded after we've determined the stellar parameters. We then used a special code to determine the abundances of our stars. And we determined in this paper the abundances of all elements starting from carbon up until europium. We did not determine the full R process abundance pattern because the aim of this paper was a data release. So the type of spectra that we obtained were what we call snapshot spectra. So we aimed to obtain a signal to noise of about 30 around 4,000 angstrom, which is where the strong europium line at 4129 lies, which we can see, I think, in figure 3. Oh no, pardon me, that's in figure 4.
That's okay, let's slide to 4. There you go.
So here in figure 4, we are showing the strongest europium line that is the main diagnostic line that we try to find in stars to check whether we have an enhancement in the R process. So the way that we aimed our observations for this paper is to try to get a signal to noise of about 30, as I said, at 4,000 angstrom, which is close to the actual rest wavelengths of this line at 4129 angstrom. And you can see that for most of the stars, we were able to observe a nice spectral line around this line. I also show the different barium lines and strontium because the barium is also a nice diagnostic for the S process, and the strontium is also a contributor to the S process. And so these three elements, the combination of them and the different ratios of these different elements relative to each other tells us what was the contribution from a pure R process that took place in the gas cloud from which these stars were formed, or whether we have contribution also, for example, from an S process or a different process. And so we then determined the abundances of these elements. In addition to, as I said, the light elements, we determined carbon, oxygen, alpha elements, iron peak elements. And you can see many of these, I think, in the last, I'm going to jump to the last figure and then come back to previous figures. Is that okay?
Yep, absolutely. Remember, this one takes a little bit to render.
Yes.
Got a lot of dots on here.
Yes, a lot of dots. And the reason I want to show this plot here is because I want to talk about how different or how interesting the production or the size of the R process is, and how it's completely independent from the formation of all the different elements that we know in the periodic table. So what I'm showing here is the abundance ratios of different elements relative to iron. So starting from carbon all the way to zinc. And we all know how these different elements are produced inside the stars. And what you can see here in the different colors are the stars that have been identified in this paper as R2, so highly enhanced, R1, moderately enhanced, and limited R, which is very slightly enhanced. And we also have identified some stars that are non-RPE, so not R process enhanced. Now you can, and we compared all of these different elements to regular Milky Way halo stars that you can see in the gray dots behind all of these different. And so you can see that most of our stars, regardless what type of our process enhancement they show, they match quite nicely with the Milky Way halo abundance pattern as a function of metallicity. So this means that we don't really, whatever produced the R process must not have affected the production of these different elements, because even the stars in the Milky Way halo that don't show any enhancement in the R process coincide very nicely as a function of metallicity where these stars lie. And so that's quite an interesting, it's quite interesting to me, I think, and it shows us how special the R process is, that it is completely different as compared to the production of other elements.
So you're using the two mass stars as representative of the Milky Way?
You mean the star and the yellow circle?
Yeah.
Oh, okay. Sorry. No, these actually have been identified as slightly interesting in terms of their chemical abundance pattern. So the black star, which is 2 mass J001, has been, as you can see in most of these panels, demonstrates or shows a lower elemental abundance relative to iron as compared to the other stars. And we flagged this star out by mentioning that it's quite different than all of the rest of our sample. And it's actually quite interesting. I don't want to give it away yet, but I think that this kind of abundance pattern that is lower as compared to the Milky Way halo stars is actually an example of what we observe in dwarf galaxies. Okay. Because there's not a lot of chemical evolution, or these are low mass systems and they are old, so they didn't have time to actually enhance these elements so much. And so this is quite interesting. We are currently writing up the paper on this star, and it's going to be exciting. So stay tuned. Stay tuned. And the other star, the yellow circle, 2 mass J052, as you can see, it matches mostly with the other stars, except for sodium, which is highly enhanced. We also have been studying this star in details, and we notice another enhancement in another element. I'm not going to give it away now because I think these two are quite correlated, but we just included here to flag it out, to say that it's different in these elements and that we are following them up now with more detailed spectroscopy. But they are both very interesting stars, so stay tuned for both of them later on. So now that we talked about all the light elements and the alpha elements and the iron peak elements, and that we didn't see anything crazy going on as compared to Milky Way halo stars, we can now show the neutron capture elements, what we obtained for these stars. So if you go to, I think, figure 5.
Figure 5.
Pardon, actually, I mean figure 6, sorry.
All good.
So the figure 6 here shows, yeah, so it shows our europium over iron abundance. And so, as I mentioned, europium is a diagnostic of the R process, especially the 4129 line, but we did determine our europium abundance from other lines as well to confirm that this is the actual abundance of the star. And this is where we naturally can see where our different groups of stars, those that are enhanced at different levels in the R process, lie. And so you can see that the highly enhanced R2 stars lie at europium over iron greater than 1 by design. This is how they have been chosen. Then we have the R1 stars lie between 0.3 till 1 in europium over iron ratio, and the limited R stars or the non-RPE stars lie at below 0.3. Now, what's interesting in this is that as compared to the Milky Way halo, which again are demonstrated by the gray circles, open and black circles behind this, you can see that the R process has been actually, it's actually similar to the R process halo, to the halo stars that which also show enhancement in the R process. But what's interesting is that they span a large range of metallicity, which tells us that the R process, so for example, the R2 spans between minus 3.2, I would say, up until minus 1.5. Sorry? Yeah. And the R1 similarly. So what this indicates is that if the R process should come from a neutron star, two neutron stars merging, or an event of a neutron star merging, it must have occurred at multiple epochs. And so this means that the R process did not only take place in one epoch, first of all, and that this also signifies that maybe there are multiple sites for the R process. And the reason for that is we know that the R process usually, from other studies that have studied the R process, it usually peaks around minus 2.5. However, we also see some highly enhanced R process stars around minus 2, which tells us that, which tells us that we also must have had contributions of maybe different events contributing to the R process. Now, this is still a work that we need to find more of these stars to have a more statistically significant sample to actually talk to this fact. But already this data release, in addition to what we call here RPA1 and RPA2, which are the other two data releases from the R Process Alliance that were written by Therese Hansen in 2018 and Charlie Sakari also in 2018, you can see that we have already increased the R process sample quite significantly as compared to what we already had before that. So in the past 20 years, the community have identified about 6 or 7 R process stars. And with the RPA, because this is such a concentrated effort, we have identified about 30 or 40 R process enhanced stars at the R2 level, at least.
Cool.
And if you look now at figure 7, we also plotted the europium abundance in an absolute sense, so the absolute abundance of europium as a function of metallicity, to show the evolution of europium as a function of time. And as expected from chemical evolution models, the R process actually, or the production of europium increases as a function of decreasing metallicity, which means, as I said before, it's totally possible that that the R process started at a long time ago, but then it kept increasing, obviously, as we expect when more and more neutron star mergers or different processes contributed to the R process. And finally, in figure 8, one other way to constrain the contribution of the R process and kind of isolated from the S process, which is also capable of producing some of the elements, some of the R process elements, such as europium, we usually use barium over europium as a way to show whether the stars have a contribution from the S process more or from the R process. And usually we would expect that stars that are mainly formed by the R process should have a barium over europium ratio below minus 0.5. And you can see here that most of our R2 stars, or highly R2 enhanced stars, have indeed this ratio of barium over europium of minus 0.5, which tells us that many of them have been polluted by mainly an R process event and not an S process event as well. Whereas our R1 stars, which you can see in green triangles here, they do show slightly larger values of barium over europium ratio, which tells us that there could be a contribution as well from the S process, or maybe other events that produce these heavy elements. Some of these events that have been suggested are collapsars, for example. Some of them are magneto-rotational supernovae, which could be also contributing to the R process. Obviously, with the R process alliance and with these types of data releases, we are trying to collect as many of these stars as possible, because our aim is then to provide to the theoretical community a very statistically significant sample so that we can test these different theories of what is the dominant site of the R process.
Cool. Very cool.
So I think this is mainly it for these samples of stars that we have discovered, or that we have identified in our data release of 3 years of work. But I think it's quite interesting. I'm proud of these stars. We all are, and we are currently working on more data releases within the R Process Alliance to increase the sample of R Process stars.
Okay. So if you look in your crystal ball, sort of where do we go as a community over the next couple of years? Or can we look forward to 10 times as many R process stars, Southern Hemisphere?
I would say not 10 times, because as you see, this effort is quite large. To give you maybe a perspective, in 2003, Paul Barclay wrote maybe one of the first papers that studied a huge number of metal poor stars and identified about, I would say, 8 or 7 highly enhanced R process stars. Since then, not many, or very, very slowly, the community has been adding to the R process enhanced stars. And only in these past 2 years, because we have been doing this very concentrated effort, we have been able to increase this from about 10 to 30 or 35 highly enhanced stars. So currently in the R Process Alliance, we want to do things as homogeneously as possible, because homogeneous is key here, the analysis of such a large number of stars, so that we give the theoretical community a really good sample to further follow up. And so we are working on some 1,000 or 1,500 spectra of, so this was only 141 stars. We're working on about 1,000 sample that we aim to release hopefully by the end of next year, which hopefully, yes, in the next 10 years, we would like to increase the sample up to maybe, let's say, 100 R2 stars. We think this is a good representative sample, but one of the other aims of the R Process Alliance is to also look in details at these stars that are highly enhanced in the R process. So we want to do what we call a portrait spectroscopic follow-up to these snapshots that we presented in this paper. So portrait means we go to the telescope and we obtain much more time to get a higher signal to noise on each of these interesting stars, which would allow us to measure the full R process pattern in each of these stars. And because the devil lies in the details, so we want to try to calculate these abundances for all the different peaks of the R process, because we believe that the scatters in the different peaks can also point us to different R process sites.
Let me ask another question on another axis. If you look into your crystal ball, when do you think non-LTE analysis will become routine?
That's a good question. This is one of my big dreams, and in fact, this is one of the goals of me and my research groups right now. As we discussed earlier, it's not a type of calculations that everybody would want to use, and I completely understand that. But I think now the approach is, rather than ask the community to perform these calculations, is to provide them with some sort of ways to apply these corrections to their.
Okay.
Yeah, and so we are currently working on something like that, basically a website to try to give to the community to obtain their corrections for different elements, their stellar parameters. As I mentioned before, non-LTE is very important, but we also have another aspect of modeling stellar atmospheres, which is the using fully three-dimensional atmospheres, and these would even add complexity to the simulations. But I think that a lot of progress has been made as well in this regard. There are multiple groups around the world, and here in the US, we're starting this as well to try to perform full 3D non-LTE analysis. So I would say maybe in the next 5 years, this will become more feasible to the community as a whole.
Cool.
Yeah.
Future is bright, so to speak. That's
Yeah.
awesome.
Thank you.
All right. Rana, I want to thank you so much for spending some time and walking us through your really lovely APJ paper.
Thank you so much for having me. It was great talking to you, Frank.
All right, everyone. Thank you, and we'll see you on the next one.